Determined.
Okay, good afternoon, everybody. Frank, I loved your talk. It's demystified TMDLs and WIPs for me in a way that no one had done before, and I appreciate you taking the time to participate with us in our first webinar. Today we're going to talk about Lyme requirements. From probably once a month I get a question from someone out there about buffer pHs or Lyme requirements, and we usually cover this topic every couple years so that people hear it as they enter into the program. Okay, first of all, what is a Lyme requirement? Essentially, it's the quantity of ag limestone that would be needed to increase the pH of a soil from where it is to the optimal pH or the target pH for the crop or the crop rotation. Many soil test labs have a Lyme requirement as part of their standard output. And of course, like any soil test, a Lyme requirement procedure or process has to be ground truthed by experiments. Field-based Lyme experiments are preferred, they're the best, and one would want to do those on selected soils that represent the range of conditions that are out there in your state or the region you're trying to serve. And those would be, it should span the range of organic matters that you encounter, clay content, clay types. Second way of ground truthing, which is now somewhat less preferred for reasons I'll get into later, but certainly more practical, is to bring soils in from the regions you're wanting your information to be applicable to and doing some soil Lyme incubations in a controlled environment. And obviously, this is a whole lot more straightforward. You go out once to collect your soil, you bring it in, you do your work on a lab bench in a growth chamber, someplace more controlled. Now, I always like to give people a sense of what it takes to do any of this. So many times people say to me, this is kind of an aside, you really need to look at this. And I'll go, yeah, well, you know, that would take some money and some time, and I'll see them a month later, and they'll ask me if we've done it yet. So I am going to spend some time over the next few minutes telling you what one of these Lyme rate field experiments would really entail, so you can appreciate the effort that would go into them. This was a Lyme rate field experiment done in Maryland. 3 Lyme materials were part of this experiment. They looked at a traditional ag limestone, a burnt lime, and a hydrated lime. They looked at 2 Lyme rates. They had an idea of what the theoretical optimum was, so they looked at what that was for each soil as well as twice that rate. They looked at 7 properties, or 7 soils that had a considerable range of properties in terms of locations, clay contents, clay types, etc. And they actually monitored the pH for the entire length of the experiment. They looked at it at 3 months, which was approximately the end of the growing season, a year later, 2 years later, and 3 years later, before they went public with their information and made any recommendations. So as you can see, this is certainly not a rapid process to get high quality data that you'd want to stake a recommendation on. So I'd like for you to use the chat box and tell me what year do you think the experiment I just talked about was initiated or started? When was the Lyme put out on these soils in 7 locations? So I'll give you about 30 seconds to respond in the chat and tell me when you think this was started. Okay, thank you for the folks who hazard a guess here. It was actually in the spring of 1947 is when the Lyme was put out, and this experiment continued through the 48 and 49 growing season. Now, this isn't the earliest lime work that was done in the country. There are published accounts of work that dated back to the 20s. So some of you that said 20 and 30s, you weren't far off. Some states were doing lime work then. But this experiment wasn't started in Maryland until 1947. And I'll talk a little bit about this, more about this experiment later this afternoon. Now, soil lime incubation studies have also been done in many locations. And this is some data from Virginia. They actually brought soils in from 17 locations across the state, each of which represented, in their opinion, important agricultural soils. They only looked at one lime material. They looked at reagent-grade calcium carbonate. They looked at one rate. They were simply trying to neutralize the exchangeable acidity. The experiment lasted 3 months. They basically moistened the soils to field capacity after they mixed the lime thoroughly with them, let the soils dry, moistened them again to field capacity at 30 days, let it dry, moistened it at 60 days, let it dry, and then at 90 days the experiment was over and they monitored the pH. Okay. Oh, now, when do you suppose this experiment was done? Anybody want to guess? Give you about 10 seconds. To type into the chat. Okay, thank you for your responses. I know someone out there is paying attention. This was actually done about 2000 or 2002 or 2003 when Virginia was switching from one lime requirement system to another. So, you know, some of the work that's done to back up the lime requirements that are put in soil test labs are quite old. They have some age on them, and others have been done much more recently. Okay, now before we go any farther, I want to be real clear about the fact that there are 3 kinds of acidity or types of acidity in soil. We have hydrogen and aluminum ions in the soil solution, and the soil pH measured with a pH meter actually measures the hydrogen ions in the soil solution. We also have what's called reserve or exchangeable acidity, and this refers to the hydrogen and aluminum that's adsorbed onto charged clay particles or charged organic matter particles. And I hope we understand that there's an equilibrium between the two, and that your reserve acidity recharges your active acidity if it goes down, like it is, for example, when we lime. So the reserve acidity is the storehouse. And that's essentially what we're trying to get a handle on quantitatively when we come up with a procedure or a soil test for lime requirement. We know what the active acidity is. The real question is how much reserve acidity is there that we need to impact on to make a long-term impact on your soil pH or your active acidity. But I also want to mention potential acidity, because we have situations in Maryland where potential acidity comes up and surprises us if we're not aware of the fact that its potential is out there. And you notice down at the bottom of the slide, now get my pointer out here. Now, pointer. Okay. Notice this little pointer down here. This refers to sulfides. And if sulfides are exposed in the near-surface environment in the aerated zone of a soil, they actually oxidize and produce acidity. Now, normally in a typical situation, we don't have any sulfides, but we do have situations where material from below the water table is drug up to the soil surface and perhaps vegetated. And in situations like that, sulfides can exist and they can oxidize. And over a relatively short to a moderate period of time, you can get substantial amounts of acidity being released. And these are not picked up in either the initial soil pH or in the reserve acidity tests that we have. Okay, so sulfides, do you see these here? Sulfides. So we've got clays, organic matter, and sulfides. There are also some areas in Prince George's and Anne Arundel County where soils that are rich in glauconitic illite and iron sulfide have been exposed during development when a landscape is reformed to make a housing development or a road or a shopping center, and where sulfide-rich materials have been exposed and where they then oxidize and produce phenomenal amounts of acidity. You'll hear the term acid sulfate soils. That's referring to soils that are highly acidic now because the sulfide's converted to sulfate. Unfortunately, there's no good test for this. Somebody would not routinely test for sulfides unless they were dealing with some very unusual situation. But if, in fact, you ever have soils that are brought up from below the water table and your plants all of a sudden start dying, do check the pH, because it could be that you're having a problem with the oxidation of reduced materials like sulfide. So a question that often comes up is, why do we say that aluminum is acid? Everybody understands that hydrogen ion is acid, but why is aluminum considered acidic? Well, the reason is that aluminum can undergo a reaction called hydrolysis with water, and that means that a material reacts with water. Essentially, it reacts with the breakdown products of water, either hydrogen ion or hydroxyl ion. And in the case of aluminum, it has a strong affinity for OH, or hydroxyl ion, and they associate with the hydroxyl, making or freeing up the aluminum. And so you can see that if an aluminum ion was released out into the soil solution during the process of weathering, for example, that I'm having trouble with my pointer here. Okay, that it would undergo hydrolysis. One of the OH, or hydroxyl ions, would associate with the aluminum, and that would neutralize one of the charges on the aluminum, and it would also free up the hydrogen, producing essentially hydrogen in the soil solution. Now that reaction, that hydrolysis, can occur 3 different times. Once with the Al plus 3, the aluminum ion, once with the AlOH. It can react also with another molecule of water, and the AlOH 2 plus 1 can react with a third molecule of water. Now, I forgot my last hydrogen over here, but when I post these slides to the web, I'll have the correct one on. Essentially, there are 3 hydrogens produced for every aluminum that undergoes hydrolysis. Now, where does the aluminum come from? It comes from the weathering of aluminosilicates, which are, the primary big family of minerals we have in our soil. So as those minerals weather, they release aluminum into the soil solution more rapidly under acidic conditions, by the way, and those aluminums undergo hydrolysis and in the process produce aluminum on a 3-to-1 ratio. So that's why aluminum is considered to be an acidic cation. So I'm going to ask you for some feedback here. We talk about the factors that affect reserve or exchangeable acidity during fundamentals training, and most of you on the list are certified consultants, and I know we do have a few certified farmers, but all of you that are certified consultants know what these factors are, or at least you knew what these factors were when you took your exam. So I would like to take about 30 seconds here, and I would like you to put in at least one of the 3 factors that affects reserve acidity. Okay, 30 seconds. Please write this in the chat. Factors affecting reserve or exchangeable acidity. Okay. Thanks. I hope those of you that aren't responding haven't fallen asleep, but yes, you're right. The predominant factors that affect reserve acidity are the amount of clay-sized particles, the type of clay, and the amount of organic matter, particularly humified organic matter. The more clay you have, typically the more you reserve acidity. The more highly charged clays you have, the more reserve acidity, and the more organic matter, the more potential acidity, the more reserve acidity you can have. Okay, so what soil property provides information about the amount of clay-sized particles in a soil? What would that soil property be? And you might find it on a soil test report, or you might not. Give you about 20 seconds here. Okay, thanks, Bill. Thanks, Krista. It turns out textual class is a piece of information that exists on many, though not all, soil test reports, and it does communicate information about the amount of clay-sized particles. And yes, CEC would too, though not perfectly and not directly. Of course, neither of these are perfect. So textual class does give you a range of clay-sized particles in the particular soil that you provided to the lab. Now, it's a range, and I think it's helpful to understand that it can be a pretty substantial range. So let's look at this textual triangle for just a moment. If you would please, and I'm going to try to get my pointer up here. If, for example, you had a soil, my pointer's not working very well. If you knew that your soil was a clay loam because your soil test lab told you that, look in the center of the textual triangle here. Okay. A clay loam has anywhere from 40% clay to about 28% clay. All right, that's quite a range. That's 12%. If you go over to the right and look at a silt loam, knowing that your soil is a silt loam is only telling you that you have somewhere between about 28 and 0% clay. So textural class is just a rough indication of how much clay you have, though as we'll see, it often is the basis of estimating reserve acidity in a number of the systems that initially were developed and may still be used to indicate what your lime requirement is. Okay, so I hope we all understand that lime requirement, that is getting a soil from a specific pH to a higher pH that's more desirable for your crop, is very much a function of your reserve acidity and is reflected by the textural class of your soil. So I'd like us to go over here to the 6.5 point. Now, all these soils started out with a pH of 4.5. All right. If you wanted to lime them the 6.5, and you had these lime response curves, and that's what we're looking at here, you could actually figure out how much lime you needed. For example, you could go up go up 6.5 directly towards the top of the graph to where it intersects the sand line. Take that over to the left axis, and you can see that to raise that particular sandy soil from a 4.5 to a 6.5, the sand takes about a ton of lime per acre. Now, if you go back to 6.5 again, and you follow it up to the sandy loam line, where it intersects the sandy loam, and proceed over to the left axis, you can see that to raise the sandy loam soil from 4.5 to 6.5 takes about 2 tons of lime. Why? More clay, perhaps more organic matter, more lime needed. Now let's do this once more for the clay loam. If you want to lime that clay loam soil from 4.5 to 6.5, go back to 6.5, go up to where it intersects with the response curve, go over to the left-hand axis, and you can see that it takes 4 tons of limestone to bring that soil from a 4.5 to a 6.5. And of course, this is one of the reasons why we always recommend that you lime based on a soil test that gives you a reliable lime requirement, and don't just go out and guess, right? Because not knowing what your potential reserve capacity is can lead you down the wrong road here and can actually lead to overliming of your soil. Okay, so let's talk about the actual methods or procedures that are out there that are used, that are or were used to develop lime requirements. The oldest methods, the methods developed by many states first off, 20s, 30s, 40s, even 50s, were based on what I'll call indirect methods. Right? We didn't directly measure the lime requirement. It was estimated based on soil properties. Okay, now we already talked about the soil properties associated with reserve acidity, And when you look at the procedures that many states use to determine lime requirement, they include some subset of these: organic matter, cation exchange, texture, clay content, soil series, or soil region. And as with many other soil tests, states didn't agree, so one state would decide that pH and texture was good, and another state says, no, that doesn't work here. We want to know our percent clay and organic matter. And another state said, no, organic matter is not helpful in this state. We only want to look at organic matter. So the methods were all over the landscape, but in fact they all hark back to some measure of reserve acidity. So there are also direct measures that methods that were developed, and the first one I'm going to talk about is the soil lime titration. It's taken on a new life in the last decade when some states are going back to this. So I'll talk first about that. Essentially, you add various aliquots of lime to a soil water suspension, let it equilibrate, and measure the pH at each aliquot of lime, and essentially construct a lime response curve like that one we just read off of. So if you look at this little picture here and go up to the top row, that top row of little cups represents, from left to right now, no lime, 1 ton of lime per acre, 2 tons of lime per acre, 3 tons of lime per acre, and 4 tons of lime per acre. All right? And the procedure that I'm showing here is the one that is still used by LSU, Louisiana State, and essentially their protocol says that you let the lime equilibrate with the soil for about 24 hours. So you set up your lime test information on one day, and you come back about a day later, and you read the pH of each one of these, plot it, and determine what your lime requirement is for whatever pH is indicated by the crop the person is going to grow. So you can see that while this is a direct method, we are actually adding lime to soils, carefully measured amounts, and looking at the pH and plotting a response curve. This has time and money written all over it. The fact is you've got to weigh out 5 aliquots of soil, you've got to wait 24 hours, you've got a lot of time, a lot of glassware. This is a slow and very, very labor-intensive process. Right? So it's a very reliable process. And when I first went to Louisiana, I spent a lot of the 80s in Louisiana and realized they did this test. My first thought was a rather uncomplimentary one because I knew in Georgia we used a buffer. And I realized after understanding the variability of soil across the landscape that they were using this because they had such massive differences in clay mineralogy and organic matter across the state that there really was no one buffer that ever would have worked for them. They had Mississippi River alluvium and Red River Valley alluvium and coastal plain and coastal flatwoods, and the properties were just so diverse, much more than in most other states, that this technique was actually a very reliable one for them. All right? So very few places use soil lime titrations, although, as I say, a state has added one in the last decade. What developed later, this is in the 50s, 60s, and 70s, were soil buffer equilibrations. And if you see a column on a soil test report that says buffer pH, it means that the lab whose report you're reading uses one of these buffers. They may or may not be out front about which one on the soil test report, but chances are on their website where they talk about their methods that they indicate which one they use. Okay? An advantage to these compared to the titrations is they typically are much faster. You can get pretty good turnaround time on your answers. So this is how it works. You mix your soil with a very carefully designed buffer solution. And what I mean is this solution is going to have things in it that keep the system from rapid radical changes in pH. It buffers the pH. And depending upon the technique you're using, some recommend that you equilibrate your soil buffer mixture for 15 minutes, and others recommend 30 minutes. So as compared to that titration we just talked about where you wait a day, These are both much, much more rapidly determined. And then after the equilibration time has passed, you measure the pH of the soil buffer mixture. And this is how it goes. The more the soil lowers the pH of the soil buffer mixture, the greater the lime requirement. So some people call these buffer pH depression methods, right? Because in fact, if you have reserve acidity, it's going to depress the pH of the buffer solution from the pH at which it was designed or initially determined. Okay, so the three historically more popular buffers are the SMP buffer, and that's made up to be a pH of 7, and it's named for the three soils people that worked on its development, Schumacher, McLean, and Pratt. And it was developed for Midwestern soils with high lime requirements. It was developed for soils that had high organic matter contents. I'm talking about 4, 5, 6, 7, medium to fine textures, and 2-to-1 clays dominating the clay-sized fraction. Now, if that doesn't sound like us in Maryland, that's because it isn't us in Maryland. Adams-Evans buffer was developed by Fred Adams at Auburn. He tried to use the SMP buffer and found that it over-limed coastal plain soils. And so he came up with his own buffer. Adams and Evans came up with a buffer. It's buffered to a pH of 8, and it was developed for southern soils with low cation exchange and small amounts of both 2-to-1 clays and organic matter. It was developed for soils with low CEC because they have 1-to-1 clays and low amounts of organic matter. Right? Then there's the Malick buffer. We not only have Malick 1, Malick 2, and Malick 3 soil test extractions for macronutrients, but Malick also developed a buffer. Malick, by the way, is from North Carolina, and he buffered his system, or his system has a pH of 6.6. So 3 historically important buffers. And even into this decade, and certainly in the mid-90s when a survey was done, more states use the SMP buffer than any other single buffer. Okay, well, let's look a little bit more closely at this buffer, because there's some important implications here that I would like to talk about. First of all, it's a mixture of chemical compounds, and essentially you want to do 2 things. You want a strong, highly soluble salt so you can replace the hydrogen and aluminum on the exchange sites and get them out in the solution where you can measure them. And you want a cocktail of compounds that reacts across a wide range of pH values. So in fact, the buffer pH that Schumacher, McLean, and Pratt developed had calcium chloride, potassium chromate, para-nitrophenol, calcium acetate, and triethanolamine, each of which buffered the system in a specific pH range. So it was a very well thought out system. Okay, and here's an interpretive table that I got from one of the soil liming monographs that Fred Adams edited, and it tells you how to interpret the SMP buffer. So this is the lime requirement as a function of 2 things, the buffer pH and the target pH using the SMP buffer. And the numbers in the table are given in tons per acre. So you can see that for mineral soils, we have 3 different options. You can lime your soil to 7, 6.5, or 6. And then for organic soils, the target pH is 5.2. I'll come back and talk about that in just a moment. So, for example, if you wanted to lime your soil to 6.5, okay, and you did the lime requirement procedure on it and you got a buffer of 6.5, you go down to where your target pH intersects with your pH buffer, and that happens right at 3.8. Okay, you'd need about almost 4 tons of lime per acre, 3.8 tons of lime per acre, to raise that soil to a pH of 6.5. Okay, so now this is a lookup table. There are also equations that one would use if they were doing this in a computerized soil test lab that would give you similar information by plugging in the right equation. Now, I'd like to point out for just a moment this column over here that says organic soils, all right, because organic soils, unlike mineral soils, don't have the same acid soil toxicity issues, particularly with aluminum. And you would never lime a true organic soil to the same pH you would lime a mineral soil. As a matter of fact, Frank did some work back in the 90s that showed that it's actually impossible to increase them to the same pH. All right. The fact is that one of the dominant reasons why acid soils are toxic, or that leads to acid soil toxicity, is soluble aluminum. It does a tremendous amount of damage to your roots. It tends to stop the root tip from growing. It tends to stop lateral branching of roots. All right. Well, organic soils just don't have the same problems with aluminum. The organic matter apparently chelates or reacts with the aluminum and keeps it from doing damage. So organic soils can be much lower in pH and still be very productive systems. So I checked with Jim Brewer over the last week, asked him, do we have any true organic soils, peats or mucks, that are cultivated in Maryland? And he indicated that we do not. We do, however, have a category of soil called mineral/organic soils, soils that are higher in organic matter than typical mineral soils that kind of hover between the two. And I think it's pretty safe to say that for that group, and we're talking here about soils that have, 10% organic matter, you probably don't want to lime them above about 6.8. They're kind of a hybrid between mineral soils and organic soils. Okay, now the Adams-Evans buffer is a little bit different. This is the table for a target pH of 6.5 only. And to use Adams-Evans, you need to know two things: the pH of your soil measured in water, which is what's typically reported on a soil test report, and also the pH of the buffer. So, for example, if our soil had a pH in water, or the typical pH of 5.7, and a buffer pH of 7.4, we need 3,169 pounds of limestone, or about 1.5 tons, to raise it to a pH of 6.5. And again, this is just a tabulated form of the data. If one were computerizing this, they would use the equation. But this essentially is telling you how this particular buffer would be interpreted. Okay, let's talk a little bit about University of Maryland's lime requirement evolution. First of all, that field work I talked about early on this afternoon was done by Hoyert and Axley. Axley was the soil chemist at the time. The publication that they put out based on their work was very interesting. It starts out by saying, quoting the 1949 Ag Statistics, which indicated that only about 220,000 tons of lime were used in Maryland. And there certainly was a feeling on their part that not enough was being used, and that they wanted some strong data to support a program to convince farmers of the value of lime. And that's why they spent time putting out this lime rate experiment at 7 locations across the state and monitoring it for 3 years. So this is oldie but goodie stuff. Okay, and here's the interpretive table that they published. This was published in the journal called Soil Science, and it was published in 1952. It was actually Hoyert's PhD work, from what I can tell. And this is the lime requirement in tons per acre for various textural classes in Maryland. And this is assuming you're going to want a target pH of 6.5. And you can see that they looked at two things. They looked at, well, what's your initial pH, where you're starting? This would be the pH in the water. And what's your textural class? And the table in their publication mentioned 3, sandy loam, silt loam, and silty clay loam. So again, if you wanted to lime to a pH of 6.5 and your pH of your soil was 5 and you were a silty clay loam, you in fact needed over 5 tons of lime, almost 5.5 tons of lime per acre to increase that pH to 6.5. Okay. So now I have a question for you. I'd like you all to wake up now, especially those folks who are extension nutrient management advisors. I want you to think about whether or not what I just talked about, using pH and soil texture, reflects the current University of Maryland protocol for lime requirement. This is just a yes or a no. I'd like to see a bunch of them, yeses or nos. Give you about 20 seconds. Okay, thank you all. And of course, the answer is no. It's been refined somewhat, and it's been refined by adding physiographic province or soil region to the mix. Okay, that was not in the initial publication of Axley and Hoyert. And of course, physiographic province or soil region gives us better information about reserve acidity because the dominant clay minerals vary from region to region in Maryland. And hopefully we all know that 10% clay on the eastern shore isn't 10% clay in Montgomery County or in Garrett County. There's certainly more highly charged clays and more potential reserve acidity in the Piedmont mountain soils. So this modification refined the lime requirement protocol that's used by Maryland. And now I'd like to take just a few lines out of SFM5, one of Frank's bulletins, and look at the lime requirement for a target pH of 6.5. And this is expressed in pounds of oxides per acre. The way the information in SFM 6.5 is expressed. And this is just the number of lines right out of that publication. So let's look at that next. And this is a snapshot of the table in that publication. You can see that down the left-hand side is your pH water. This is the pH in a soil solution, in a soil-water mixture. Your textural classes are across the top. For some textural classes, region has no relevance. For loamy sand, it doesn't make any difference which region you're from. But for the heavier textured soils, the loam, silt loams, clay loams, you interpret the information differently for coastal plain than you would for Piedmont and mountains. And you can see that the lime requirement is higher for the same textural class. Let's look at loams. If you have a soil whose pH is 5.5 and it's a loam and you want to raise the pH to 6.5, it only takes about 2,000 pounds of oxides in the coastal plain, but it would take 2,500 pounds of oxides in the Piedmont and mountain. Right? Now this again assumed the target pH is 6.5, and remember that this is pounds of oxides. Okay? So just to kind of sum it up, University of Maryland Extension Soil Testing Lab estimated lime requirement by a combination of pH, target pH, soil texture, and physiographic province or soil region. And these tables codifying all this are published in a bulletin called SFM5, and that's on our website if you don't have a copy at hand. And there are 4 different target pHs in each of the separate 4 tables in the back of this publication. And this is the method that's programmed into Newman Pro. So one of the reasons on the field page of Newman Pro that it asks you for your soil region is so that it can give you the right information. You tell it the crop. It knows what the target pH is from the crop because that's programmed in. You tell it the pH and the soil texture on the soil test page. And so with those bits of information, it generates a lime requirement for you. Okay. Now here's the question. I'll give you about 30 seconds to answer this. Why do some states have no lime requirement procedure? Okay, about 20 seconds. Why is that? You're awfully quiet out there. Well, the answer is they don't need them. They don't have any acid soils, so they don't have any acid soils that they need to amend. And these are states like Arizona, New Mexico, both the Dakotas, Nevada, Wyoming, Utah, Montana. These guys actually have calcareous soils in many states. In many cases, they have soils that actually have solid-state calcium carbonate in them, and they already have pHs up in the 7s and 8s, and they don't need to lime. So it's not a standard offering among soil test labs that serve this part of the country, particularly the land-grant labs at these universities. Okay? Don't have them because they don't need them. They have other tests they do need that we don't do, but they don't need a lime requirement test. Okay, so soil testing, particularly for lime, really collided with what we call RCRA, You're probably not familiar with that. I hope you're not familiar with it. It's the Resource Conservation and Recovery Act that Congress passed in 1977 and amended in 1976 and amended in 1980. It basically governs the use, production, transportation, disposal of anything that's hazardous. And the 1980 refinement of the bill actually listed a huge array of chemicals that were deemed to be hazardous. Unfortunately, some of the stuff being used in soil test labs was on that list, particularly the things that were used in the buffers. So the SMP buffer actually won out with the honor of containing two hazardous materials, para-nitrophenol as well as potassium chromate. Potassium chromate was also listed as a human carcinogen. The Maluk buffer had barium chloride, and barium salts were considered to be hazardous. And para-nitrophenol, of course, was used also in the Adams-Evans buffer, and it was listed as a hazardous material. I can't begin to tell you what heartache a user of a hazardous material has. They have to get a permit that tells exactly what they're using it for, how it's stored, how its use is being monitored, go through training of their staff. They have very detailed records they have to keep. They have to have manifests when they dispose of it. They are subject to inspections without notification to look at the records and to make sure that the hazardous materials in storage are locked down. It's not something you want to put yourself through if you don't have to. And in addition to that, you just can't throw out a RCRA waste in the dumpster. Hazardous waste have to be disposed of in a special type of landfill called a hazardous waste landfill. And disposal of any material in a hazardous waste landfill is hugely expensive compared to ordinary disposal. So when soil test labs realized that they came under the guise of the jurisdiction of the EPA under the RCRA statutes, many of them decided that they needed to look at their Lyme requirements and their Lyme procedures and see what could be done to get them out of that group of people. And so, of course, folks had Lyme requirement procedures that they were used to. Their users were used to them. But essentially, labs wanted reliable and comparable Lyme requirement procedures that did not contain hazardous components in the buffer. So there was a whole new round of investigation that took place in the late 90s and early parts of this last decade. And there was actually a special session at our national meetings in 2005 about Lyme requirement procedures, where everybody shared their work to date and talked about how they had responded to what was really a crisis. You know, when you're a fairly borderline operation in terms of profitability, and all of a sudden you have $100,000 a year bill for your hazardous waste disposal, you're gonna do something about it. So it led to a new round of soil Lyme incubation studies, to ground truth, the changes people were envisioning. It led to a number of states comparing the method they had been using that had a hazardous material in to a different method that didn't. It led to development of new and modified Lyme requirement buffers. And in the past 10 years, many states have changed to a Lyme requirement buffer. It's about time someone does another survey. I would hazard to guess that for example, that very few labs now use the SMP buffer, even though in 1995 it was used more than all other buffers combined, because it contains two hazardous materials. Okay, so some of these changes, Georgia, for example, changed from Adams-Evans to a 2-point titration. Several people got graduate degrees from Georgia working with Miguel Cabrera, looking at a 2-point titration and even a 1-point titration that was only incubated for 30 or 45 minutes, and they came up with something that's made them happy, so they've switched to that. More and Sakura buffer has been developed. Sakura runs a soil test lab in Kentucky. They've been using Adams-Evans, so he went ahead and did a very elaborate study to come up with some different buffers, and now it's named for he and the person who did the work with him more. Maluk buffer was modified. Some folks showed that instead of using barium chloride to exchange your hydrogen aluminum off the exchange phase, calcium chloride worked just as well. Of course, the barium chloride killed the fungi, so you had a long shelf life of your reagent. That's no longer true with calcium chloride. So the modified malic gets gunked up with fungus first, and they modify the pH of the solution. It means that the labs have to check their buffer pH every day before they use it to make sure it isn't colonized by fungi yet and the initial pH hasn't been modified. And at this point, it looks like many people have changed in the direction of using the modified buffer. Of the states that I can access information about, many of them who used to use the SMP now use the modified malic, the malic that has calcium chloride as the major exchanger instead of the barium chloride. Pennsylvania, for example, did this, and they've recently published a very nice article that showed how they compared the lime requirements from SMP and malic, and they ground truthed it against the soil lime incubation study, and they're very happy with the malic numbers. And Virginia uses malic now. Virginia Tech uses it. They actually used an indirect method where they used soil pH and texture until the early 2000s, and they now use the malic buffer. So many states have now gone to malic because in its modified version there are no hazardous materials. They can bypass the RCRA permit. They can bypass the expensive hazardous waste disposal. So lime requirements may seem like a pretty dull thing, but boy, the top just came off the lid in the late 90s when labs realized they were subject to the RCRA regulations. Okay, so things to remember if you're either selecting or interpreting a buffer pH. The older method should probably be avoided if you don't want to pay hazardous waste disposal costs and go through the RCRA permitting process. If you can get comparable information from a modified malic, I don't know why you'd still hang on to the SMP. And in fact, most labs that I can access information about haven't. But I also want to emphasize that the buffer that one is using to make lime requirements should be appropriate for the soils in the region where their clients are being served. And historical work clearly showed, Fred Adams, for example, showed that the SMP shouldn't be used on coastal plain soils. It over-limed the soils. And in case you don't remember, that is not a good thing. And there's also a study that showed that Adams-Evans isn't good on soils that have moderate to high CEC and high 2-to-1 clay content. So just like phosphorus tests might be good or bad in a specific region because of the phosphorus chemistry, a similar thing is true about buffer pHs. On the other hand, the malic appears to be quite adaptable. Virginia's work showed that even though they have the same array of soil provinces and CEC that we have in Maryland, they found that the malic serves them quite well across the regions. Pennsylvania was the same way. They compared malic to SFMP. They've got a number of physiographic provinces too, and they found that the malic served them well across those physiographic provinces and those soil properties. So the malic appears to be a little bit more adaptable than either SMP or Adams-Evans based on my observations. Okay, I know this is a little dry compared to Frank's talk, but again, questions come up on this periodically, and I thought